Okay, so I hope you can see the slide already. So we have covered everything regarding constant volume batch reactor data, and we have covered both integral and differential analysis. Now for this afternoon, we'll be discussing varying volume batch reactor, and it's also divided into two parts, the integral and differential analysis. So the part on differential analysis will just be discussed. It will not be given much emphasis because just like the differential analysis for constant volume batch reactor data, it's relying heavily on graphical procedure. So we will rely on the analytical procedure, which is the integral analysis for varying volume batch reactor. Okay, let me proceed to the next slide. Now, this varying volume batch reactor is primarily used in the microprocessing field, where, as an example, a capillary tube with a movable bead would represent your reactor. So there's a bead inside this capillary tube, which is likened to that of a plug flow reactor, but this time we look at it, or we interpret it as a batch reactor with varying volume. Now, it's also used, the treatment of varying volume batch reactor data is also used for isothermal constant pressure operations. So again, it has to be isothermal, meaning constant temperature, because our rate constant will be varying if temperature is changed, and constant pressure operations. So both this time, the temperature and the pressure are kept constant. And this time will not be anymore covering multiple reactions and reactions which have more than several steps to consider. So in this case, we'll only be talking about interpretation of varying volume batch reactor data for a single stoichiometric equation. So meaning we only have a single reaction to look into. So no multiple reaction in this case. Okay. Now let's look into what will be the major difference between the integral analysis for constant volume and varying volume batch reactors. So you will see it here on the next slide. So since volume is varying, then we need to have a formula or an equation that will allow us to determine how will the volume behave over time or as the reaction proceeds. So in this case, our volume has a linear relationship with conversion. So you could see in here that the volume of your reaction fluid or your system at any particular time is equal to the product of the initial volume, P sub O, and the quantity 1 plus epsilon A XA. So XA here is the conversion, the degree of conversion of your species, which is A, the reactant species, which is A. Now, from this particular formula class, you can derive the formula of the conversion, this time based on the change in the volume. So you can see here, final minus initial volume divided by the product of the initial volume and epsilon A. And we will have a different representation for the differential of the conversion taken from this particular equation. So if we take the derivative of the left side and the right side of this equation, then it would be dxa. And this part here with differentiated will give you dv only, because the derivative of a constant b sub o, it's a constant because it is the initial volume, will be a 0. So these two in the denominator are constants, your initial volume and your epsilon A, so they are just simply copied. So what you are differentiating here actually are just the variables, the parameters that vary over time. So in that case, that would be conversion and volume. Now this one is taken from this. So the dxa expression is taken from xa expression, and the xa expression or equation is taken from this linear relationship between volume and conversion. Now you see a new characteristic parameter here for varying volume systems, and that's the epsilon A. We call it the fractional change in the volume. Now, how do we determine the fractional change in the volume? So we take the volume when everything is converted, when all your reactant has been converted, on the assumption that you have 100% conversion, minus the volume at zero condition. So this volume at zero conversion rather. So this volume at zero conversion is actually your initial volume, equivalent to your initial volume. So the final volume at 100% conversion minus the initial volume over the initial volume gives you the fractional change in the volume, which is epsilon A. Okay, so you will have this formula to take note of. So I'd like to emphasize you'll be needing this formula, and so is this formula here for the linear relationship between volume and conversion. Anyhow, the two formulas that you see in here below this volume in terms of conversion equation are just derived from it. So you just need to take note of these two equations here. Okay, volume and fractional change in the volume. Moreover, this will be the corresponding change as well in the manner we determine the concentration of A after some time. The concentration of A after some time when you have a varying volume batch reactor. Now, we are used to the basic formula for determining the concentration of A after some time when it is constant volume. And it doesn't have this expression here. Okay, so it's just CaO 1 minus XA. So in the case of varying volume systems, you need to divide your original formula by 1 plus epsilon A XA. Now the formula that is shown here below, this one, which allows you to determine the degree of conversion given the changes in the concentration and the fractional change in the volume, is just simply derived from this one. So I'm emphasizing it because there's no need for you to memorize this particular formula because it just came from this. But if you intend to, that way you will not have to derive from this particular equation, then do so. So this is now your new formula for the concentration of reactant A after some time, and this is your new formula for the degree of conversion. Now, you may ask, you have a formula for the degree of conversion in the previous slide, which is in terms of the change in the volume. You have actually two formulas for XA. So you need to select which of the two formulas is applicable based on the data that the problem gives you. So you cannot use the formula that determines the conversion based on the final and initial volume if those two informations in the first place are not known or were not given to you. Oftentimes, the given data is in terms of concentration, initial and final concentration, and you need only to determine the fractional change in the volume, which we will also be discussing in a little while. How do you determine the epsilon A? But if the problem already gives you, okay, let me clear my marking here. If the problem already gives you the change in the volume, you can use this particular formula. Let's say, for example, the problem gives the change in volume over the initial volume, or the problem gives you the change in volume with respect to the initial volume, then you can use this particular formula in A. So you just choose which one is more applicable depending on the provided information. Because this one could be the fractional change in the volume. And there are problems actually, class, that gives the change in the volume with respect to the initial volume. So this entire expression here can be represented by just one thing. For example, the change in the there is a 50% decrease in the volume. So if there's a 50% decrease in the volume, so we say that this one would be 0.5, okay, or negative 0.5 V sub O. So the V sub O will just cancel out. Or there's a 50% increase in the volume. So you will have 0.5 V sub O over V sub O. So the only thing that you need to determine is the fractional change in the volume, which is actually based on the stoichiometric equation. Okay, so you need not worry about epsilon A because you can determine it from the given stoichiometric equation. Okay, so you use this formula when you're given the change in the volume. If not, then you use the other one that was discussed in the next slide. So I'm referring to this. And this one was just derived from this formula for the concentration of A after some time. Now, when we write our rate equation for a reaction wherein the system is varying volume, so the system varies in volume. So instead of writing negative dCA dt as simply negative CaO dXA dt, if you recall, we only have it like this. If it's constant volume, I hope you can still remember. If it's constant volume, batch reactor data, negative dCA dt is just CaO dXA dt. Now, if you have varying volume, just like what you did here for the concentration of A, so you need to add or you need to place in the denominator the quantity 1 plus epsilon A XA. Okay? This one, the negative dCA dt should be replaced by this entire expression, meaning the left side of your rate equation should be replaced by this. Not CaO dXA dt only, but rather this entire expression. Now, another way of expressing the rate as well is the one that you see in here below, wherein your negative dCA dt is expressed this time in terms of the change in the volume. So I like to annotate here. This one you use when you have been provided or your problem gives you conversion. So this will be the left side. But if the problem gives you changes in the volume, so you'll have here this one, which is also equal to this one. So the d of L and V dt, L and V in the sense that you have here dV over V, so that's L and V, and you have here dt, and you have CaO epsilon A set aside. You use this again if the problem gives you a pair of volume data, that is initial and final volume. Okay, but if the problem gives you changes in conversion, you use this. So the left side actually will depend on what the problem gives you. At the left side of the rate equation, I'm referring to that. The left side of your rate equation for whatever should be written on the right is dependent on what the problem gives you. Most often, class, you use this one. But there are times that you would be using this if the problem gives you volume data. Okay? Now, let's look into, if there aren't any questions here, how will then the equations or the formula for first order, second order, and zero order reactions be for varying volume batch reactor? So that should be shown in that will be shown in here on the next slide. So we're now going to look into the integral analysis, and we're going to look to each of our irreversible reactions. If it's a zero order irreversible reaction, this will be your formula. This will be your formula for determining what the problem requires from you. So you can change this V here, the final volume, in terms of V sub O 1 plus epsilon A XA if the problem gives you conversion. But if the problem gives you the final and the initial volume, then you may stick to the original formula. Okay, you may memorize this I will be suggesting this one, that you should have your notes and you should have a summary of formulas that you can get back onto whenever there's a need for you to look into the formulas that will be suitable for your given problem. So you summarize all the formulas that were given to you. It's really important that you should have your notes. All the more because should something happen to your laptop or to your desktop computer, you will have your hard copy of your notes. It's not on the desktop or your computer. Okay, and it's really guiding and easy access because you have summarized already your formulas, so you know where to look for something rather than having to click everything there in your desktop and look for the formula that you need. So this will be for the zero order irreversible reaction. If it's first order class, this will be the formula. Your delta V here is final volume minus initial volume. And again, you see that we have already volume C because the volume of the system changes. And oftentimes, 100% of the time, this is for gaseous systems. So constant pressure systems or gaseous system. If the problem is not saying that it's varying volume, but it's a gaseous system, or even if it's not a gaseous system, if it's stating that it's a constant pressure, then automatically class, it's a varying volume batch reactor system. And you have to use the corresponding formula for such a system. So for first order reaction, this will be the formula. Okay? And we have one for the second order system, but we have limited it only to elementary second order irreversible reactions in here. So it could either be a single species, so this is still second order, or you can have two species with this special condition that the initial concentration of the species are equal. If your stoichiometry is A plus B giving you the products, but the initial concentrations of your species are not equal, then this particular formula that is shown here is not anymore applicable. So it's only applicable to these two types of second order irreversible reactions. Okay, so again, you see here the epsilon A, just like in the first two formulas for zero order and first order, you see also the change in the volume and the initial volume. This is for a second order irreversible reaction. Okay, now for differential analysis, so that's it class. As mentioned at the start of the slide on varying volume systems, we are not applying it anymore to multiple reactions or problems in which you have to follow through the changes in your reacting species by more than one reaction. So that is why we have very short application only for varying volume system because it's only limited to a single stoichiometry system. Isa lang ang provided na reaction. So kung magsubra na sa isa, we don't anymore cover it in here. Okay? Now, for differential analysis, still on varying volume system, there will be changes, of course, in the manner in which you're going to plot what you need to plot. But just for discussion purposes, you will have an idea. It should be this one asked in the form of a concept type question, you would know. So the treatment is the same as that of the constant volume system, except that class, the slope of the chosen concentration, which you have taken from the curve which you have drawn by eye or by hand. So you have drawn a curve to represent your C sub A versus T data. Okay, that's the first step always in differential analysis. Then you have to choose a point on that curve, and that particular point has a corresponding concentration. Okay, as discussed yesterday. So you need to determine the slope of that curve at that particular chosen concentration. So in constant volume batch reactor, the slope of that particular tangential line in your chosen concentration would be your dCA dt. That's your dCA dt, or that would be your RA, which you need to get the ln of, together with the ln of the C sub A. That way you can find the rate constant and the the order of the reaction as our discussion yesterday. So this time you change the slope to this one. So the dCA dt is replaced with CAO dV over V epsilon A dt, which is equivalent to this actually. The dV over V is the ln of V, the d of the ln of V, and this CAO over epsilon A was just copied. So the slope will not be just dCA dt, but this one. And what you're going to plot for varying volume reactions or varying volume batch reactor data is the ln of V versus T. Okay? You are going to you're not going to plot this one, but you're going to plot the ln of V versus T to get the order and the rate constant for your given reaction, which has, as we have said yesterday as well, which has more than 15 data points, or let's say 10 data points, because 15 is already too large for integral analysis. So if your data points exceeds 10 already, it is suggested that you use differential analysis. Okay, and that ends class interpretation of batch reactor data, with the main goal of determining the what, the order, and the rate constant for a particular reaction. So the entire module is about how to interpret data done to a series of experiments. That way you'll be able to determine the rate law or the rate equation that will represent your reaction. And of course, everything follows after that. So if you have the rate law, you can determine how much is left after some time, or what is the conversion after some time. Now, since we still have time, I'll go to our book and check on sample problems which we can solve regarding the application of varying volume batch reactor data based on the formula that is provided. Okay, I will just stop sharing for now. Allow me to share Levin's field. We have this. We're going to look for a problem which will be an application of varying volume batch reactor. Okay, so I think I'm on this page. Can you see the book? I'm on problem 3.29.
Yes, Miss.
So you have there in problem 3.29, a first you are to determine, you are to find the first order rate constant for the disappearance of A in the gaseous reaction 2A forming R, if on holding the pressure constant, the volume of the reaction mixture starting with 80% A decreases by 20% in 3 minutes. Now, there are a lot of things here that tells you that you really have to use the formulas for varying volume batch reactor. Number one is this: you're given a gas reaction. So that tells you that you are to use those formulas. And another one is on holding pressure constant. So these two tells you that this is not an ordinary constant volume batch reactor system, but rather a varying volume batch reactor problem. So I'll take a picture of this and we'll solve this one based on the formulas that we have discussed a few minutes ago. Okay. So I will clear my markings here. That's it. So I hope so you can follow to in that discussion. You're also taking pictures there from your end of the problem. That way you will understand why I have written the given information as I have written it. Okay, so we're going to process 3.29, and 3.30 says find the first order rate constant for the disappearance of A in a gas reaction again. This time you have A forming 1.6 moles of R if the volume of the reaction mixture starting with pure A increases in 4 minutes. So there is already an increase in A in the volume starting with pure A increases by 50% in 4 minutes. Okay, so there is a change in the volume if that is the case. The total pressure of the system stays constant. So total pressure is constant. So as such, it's also a varying volume batch reactor system. Give me a few moments, class. Thank you. So we are starting here on problem 3.29, and the problem already starts with the direction in which we are to solve the problem. Find the first order rate constant. So n must be equal to 1. Now the stoichiometric equation follows. So 2a is converted to r. That's it. And pressure is kept constant in this case. It was also mentioned. This one is a gaseous reaction. It was also mentioned. And it says here the volume of the reaction mixture starting with 80% A. So initially, system is 80% A. Okay, this is very important. You cannot neglect this one because then you are not starting with the pure system, meaning you have 20% impurities. So you're not having a system which is all 100% A. Okay, so this is where our system is starting on, and there is a decrease by 20% in the volume. So the phrase is the volume of the reaction mixture starting with 80% A decreases by 20% in 3 minutes. So at time equal to 3 minutes, how would you translate this? Volume is, says here, decreases by 20%. So what is your volume in terms of the initial volume? If it decreases by 20%, what's your final volume? If the statement is it decreases by 20%. Again, I will read. The volume of the reaction mixture starting with 80% A decreases by 20% in 3 minutes. So what is your final volume in terms of the initial volume? Correct, Albert. So it should be 80%. It should be 80% of the initial volume because there's a decrease of 20%. Now, if you wrongly represent the final volume, everything that you will be doing is wrong. So you have to really be very careful when you assign the final volume in terms of how the problem describes it in reference to the initial volume. So Albert is correct. So your final volume is 80% of the initial because there is a 20% decrease in its value. Okay, so the required information here is you will find the rate constant. Okay, you are to find the rate constant. Now, in solving the problem, it always helps that you start with the formula because somehow you would know what you are going to look for. This is a first order varying volume batch reactor data, and we have the formula already for its for integral analysis applied to first order varying volume batch reactor problem. And that particular formula is, so I'm going to copy it in here, negative ln of, so we write here, negative ln of 1 minus, check, delta V over V sub O epsilon A. And your right side here is KT. Okay, that's our formula. That way we are guided on what we are to look for. So this is your formula for a first order varying volume problem. Now, let's look into what we already know and what we need to find. So in terms of what the problem gives us, what do we already know? I'd like to go back on the given, that way you can tell me what do we already know. This is our formula. What do we already know? We know we don't know anything. We don't know the initial volume. The problem does not give us the initial volume. Look at what the problem gives you. Okay. We know the T. We know the T. We know the stoichiometric ratio. We know the T. What is paired with this T info? What is paired with the T info? That's the given. What else do you know together with the T? Do you know the V? Correct, V. Yeah. You know the V in terms of the initial volume. So I'd like to place here that we know already delta V. If you're saying, how is that, Miss Ali? Now, remember, your delta V, the change in the volume is equal to the final minus the initial volume, right? So your final volume, given already, your final volume is 80% of the initial. So I will have here 0.80 V sub O minus V sub O. So then, my delta V, in this case, is 0.20 V sub O, but it is negative because I have here 0.8 minus 1. So that's negative 0.20 V sub O. Now, since it's already in terms of V sub O, then it even eliminates my problem here in the denominator, which actually requires me to have the V sub O. Since my delta V is in terms of V sub O, the V sub O in here and this V sub O in here will just cancel each other. Okay? So we're good with that now. So for me to be able to, so remember we are after this one. We are after the K, the rate constant K. So how do we find the rate constant K? We can find it using this particular formula of ours with just one limit, with just one more problem for us to take care of. And that is the fractional change in the volume, the epsilon A. Okay, so I'll go to the next page and explain what is epsilon A and how you're going to find it. So epsilon A is the volume of your system at 100% conversion minus the volume of the system at 0% conversion over volume of the system at 0% conversion. Now, I also mentioned a while ago, so I write it here, that this volume of your system at 0 conversion or 0% conversion is actually your initial volume. So, you have the initial volume there. So, what remains for us to determine is the volume of your system at 100% conversion. So, how do I determine this volume of your system when we have 100% conversion? Now, we go back to our problem. And let's be very careful on how we determine the volume, the total volume of your system at 100% conversion. It says here that initially your system is only 80% A. So meaning your initial volume initially is just 0.80% A. So I will have it here. I want to know the corresponding volume of R that will be produced with this available A. Again, so my system is just 80% A, so that is why I wrote here only 0.80 V sub O because my initial volume is not all composed of A. I have impurities there. From this 80% of the initial volume of my system, I will produce a corresponding volume due to, or I will have a corresponding increase in the volume due to the formation of R. Now, where will I get that particular volume due to R? I will get it in here from the stoichiometric equation. So this is what we're going to do. This 0.80 V sub O, we divide it by 2 because that's the coefficient of A. And now I will determine the volume due to R. And that would be divided by 1. Why 1? Because we have this stoichiometric equation 2A forming R. From in here, I'll be able to determine what would be the corresponding increase in the volume of my system due to the formation of R, or how much of my system's volume, of my system's final volume will be due to R. So I'll be getting now V sub R. So V sub R is equal to, you have this one, so you have 0.4 V sub O. But this one is due to all the A that has been converted to R. What about the inerts? We have 20% inerts. It says here 20% impurities or 20% inerts. They are not converted in the process of the reaction. So then, therefore, we say, therefore, the total volume of your system at 100% conversion of A, this is your A. It's all now converted to R in here, as we have determined the corresponding volume for that. So will be equal to this one, plus that part which is due to the impurities or the inerts. So I'll place here V sub XA equal to 1 will be now equal to 0.40 V sub O plus the inerts or the impurities, which is 20%. So all in all, when all the A in your system has been fully converted to R, the system will have 60% of its initial volume. Okay? Why? Because ang imo nga area 1 mole ang na-form, 2 moles ang A ang iyagin consume. So there's a decrease in this particular volume of your system. So now you can go back to epsilon A and you will have 0.60 V sub O minus V sub O. By the way, it's in here. It's written in there. So I'll just place it in there. So this 1.60 V sub O minus V sub O over V sub O. So this is 0.60 minus 1 is this is 0.4. Okay? The V sub O in the numerator cancels with the V sub O in the denominator. So 0.4. Now, since you know it's already 0.4, you can go back to this equation. So you have negative ln of 1 minus, so this is minus, so I'll make it plus 0.20 V sub O over V sub O, hindi negative, miss. Yes, it should be negative. Thank you. So we'll make it negative. So this is equal to negative 0.5. Okay? Go back where we are. So I have substituted already negative in here, so that makes this negative sign, minus sign here positive. My epsilon A is negative 0.4. I have K, and I have here the time, which is, I think, 30 minutes, or it's 3 minutes. Let me just go back. 3 minutes. So we have 3 minutes. So from in here, class, I'll just write in here, your K is equal to, so you get to cancel the V sub O's. So your K will be 0.231 per minute. Okay, so 0.231 per minute. So this is the answer. Okay? Have any question? Okay, there's none, so we'll proceed with 7 minutes. I need to discuss this one so that you will know what about if it's a different scenario. So we'll go to the next problem, which is 3.30. Write the given. Find the first order rate constant. So this same working equation will be used in here because a reaction is first order. For the disappearance of A in the reaction A forming 1.6 moles of R, if the volume of the reaction mixture starting with pure A, so starts with pure A, so there are no inerts, the volume increases by 50% in 4 minutes. So at T equal to 4 minutes, volume increases by 40 or by 50%. So then it must be 1.5 V sub O. It increases by 50% in 4 minutes. The total pressure of the system is constant at 1.2 atm. And same with the temperature. So I place here, temperature is equal to 25 degrees Celsius. The same required information, the K. So then, since this is a first order reaction, your working equation will be similar to the first one, but you have a different condition here. You are starting with pure A. So ln of 1 minus delta V over V sub O epsilon A equal to KT. So this would be our working equation. Now we'll check what we already know. There's a way for us to know this because we know the final volume. We know the time, it's stated in the problem, so we need this one. Then the only thing that we need to determine is epsilon A. I intently solve this problem last because this is easier than the first one. Whenever a problem for varying volume system mentions that your system starts with the pure reactant, meaning there are no inerts, the process of determining the fractional change in the volume is even simple. So your epsilon A here, volume at 100% conversion minus volume at 0% conversion over volume at 0% conversion will be solely dependent on your stoichiometry. So there's no need for you to do the ratio thing that we have done in the first example. So what do I mean with stoichiometry? So that would simply be the total coefficient of the products minus the total coefficient of the reactants divided by the reactant. Okay, so in this case, it's just 1.6 minus 1 over 1. So your epsilon A in here is equal to 0.6. Then you can solve the delta V. So your delta V, you have 1.5 V minus V sub O rather over V sub O. Okay, you have placed it here, 50% increase. So then your delta V is 0.5 V sub O. Then you can substitute everything on the formula. So you have negative ln of 1 minus, so you have here 0.5 V sub O over V sub O, and epsilon A is 0.6. So you have here 0.6. And the K and the time, which is 4 minutes. Okay. And that's it. You get to cancel the V sub O's, you get to know the K. Okay, what's the value of the K? 0.448. So you have 0.448 per minute. Okay, so that's it, class. You go back to the derived formula already available for zero order, first order, and second order reactions for varying volume systems. And then from that formula, look for the required information. The complexity here is toned down, reduced, because for varying volume systems, it's only limited to single stoichiometric problems. So you are not given a problem wherein there are several reactions that are happening. You're not given multiple reactions, so only single reactions are given. Okay? So any question for varying volume systems? Our interpretation for such will be limited to integral analysis. So we'll not be focusing on, will not be anymore solving problems using differential analysis. Any question? Okay.
None, miss.
Yes.
None, miss.
Oh, none.